simple harmonic motion. It's going to be one of the simpler units, but it is not the most intuitive. So I do recommend that for this unit and the next one, out of all of them, you do some practice. Khan Academy has pre-practice problems. I'm going to leave that linked in the description. Also, you have questions, you need some extra help, you need to work out a problem, etc., etc. I've got a Discord server I run. If you need help, please join. Otherwise, let's get right into it. So what is harmonic motion? Okay, harmonic motion is motion that oscillates, that continuously repeats, that behaves in a cycle. So a perfect example of that is one of the examples I cited in a previous unit video, where I have a marker at some height above the ground, and at the bottom of the marker, just below the marker, on the ground is a spring, wherein I drop the marker from the height, falls to the ground, hits the spring, compresses the spring, and the spring shoots it back up, and the marker falls back down, hits the spring, spring shoots it back up, etc., etc. That would be an example of harmonic motion. Motion in which an object is moving in a predictable path in a regular repeating scenario, okay? And in the physics course, we are going to be particularly examining two main types of harmonic motion. That will be harmonic motion with the pendulum and harmonic motion with the spring. The spring can either be seen as acting in the y-plane, meaning up-down, or it can be seen acting in the x-plane, side to side. Okay? So let's start with the pendulum. Well, let's picture a pendulum for a minute. What does a pendulum look like? A great example of a pendulum would be in a grandfather clock or a cuckoo clock, where you, as it would be aptly named, you have a pendulum swinging from side to side constantly, and that is the mechanism by which the clock ticks. Okay, so we have a point, a fixed point up at the top, we have a string connected to that point, and we have some item with mass at the bottom of the string, okay? And if I were to pull this mass up to the left side, and I were to release that mass, the mass would swing back and forth, and it would continuously swing, okay? Now, the central assumption here in harmonic motion is that we are ignoring friction. So, like I was saying before, when you release the pendulum from rest at some point that is not point A right here, it will move to the right, then to the left, and it will continuously oscillate. All right? The other example would be springs. So, like I was saying before, you could have a spring in the y-plane that is vertical with a mass on the bottom of it as such. And if I were to pull this mass downward, I pull the mass downward, the spring would pull the mass up, and the mass would move beyond point A, and then the spring would force it back down, it would move past point A again, and it would continuously oscillate between those 2 points, connected to a mass that is resting on a frictionless, smooth surface. I pull the mass this way, stretch out the spring, or I can pull the mass the other way, compress the spring. The spring is compressed, it launches the mass forward, the mass passes point A, and after it passes point A, the spring becomes stretched, pulls the mass backward, and now we have an oscillation between those 2 points. Those are the examples of harmonic motion that we're going to be seeing in this unit. Conditions of harmonic motion are described using roughly 2 main components, 2 main quantities, okay? Those 2 quantities are called the amplitude of the oscillation and the period of the oscillation. Let's continue using the horizontal example, okay? If I were to, when the block is at rest at point A, if I were to pull it back, let's say 20 centimeters to point B, the block would start at point B, the spring would pull it, the block would accelerate, it would accelerate through point A until it finally stops at a point negative B, if we assume that point A is 0, okay? So in simple harmonic motion, the distance which I would be pulling the string, or the spring, excuse me, the distance which I would be pulling the spring is equal to the distance it would travel during each oscillation. Okay, if I pull it a distance b in one direction, it will achieve a distance b in the opposite direction and will return to the original distance b. Amplitude, in this case, would be our distance b. Amplitude defines how long the oscillation is, long in terms of distance. Over what distance are we oscillating, okay? So if I were to instead bring it out further to point C, we would have a larger amplitude being C. Now, of course, C would be measured in meters because it's a length. And as we will see later through some of our equations, we will see that amplitude is related to the total energy of the system. And again, we'll come back to that later in the video to discuss why. But for right now, we're going to think of amplitude as amplitude is the distance from the center that our object travels during each oscillation. Okay? The other quantity, period, stipulates, well, the question that period asks is, how long does it take my object to complete one oscillation? Okay? Now, what do we define as one oscillation? One full loop. Okay, so if I started at point C, one oscillation would be me going to point negative C and then turning around and arriving back at point C. Okay, that would be one oscillation. It could be a little tricky to define one oscillation if, let's say, you are starting at point A, which would be our distance 0 in this case. So if my reference point is point A, one oscillation would be defined as me going from point A all the way over to C, coming back around, going back to negative C, and then arriving back here. Okay, that would be one oscillation. The reason for that being is that an oscillation is defined as the time it takes for you to return to the same point with the same velocity. Okay, so if we're looking here, when we start at point A, we travel to point C, and then we come back. We arrive back at point A, but initially our velocity was in this direction, and the first time we come back, our velocity is in the opposite direction. So the oscillation continues through point negative C, and then the second time we arrive back at point A, we arrive there with the initial velocity vector that we started with. So that would be one complete oscillation. And so, like I was saying, the period of oscillation, the period, is the time it takes the object to complete one oscillation. So now that we understand the main quantities, let's discuss the equations that we're going to be seeing in this unit, okay? And there are a few new ones. We are also going to be making use of some old ones, like I referenced with amplitude relating to the total energy of the system. So the first equation that we're going to look at on our equation sheet is going to be just below the gravitational potential energy equation on the right hand of the sheet, and that will be that period, which is capital T, equals 2 pi over omega, which equals 1 over f. Okay? What does that equation mean? Well, T, like I said, represents period. We discussed what period is. 2 pi is just 2 times the number pi, so it's a constant. Omega. What is omega? If you guys are confused, this thing that looks like a W is a lowercase Greek letter omega. And I will be calling it omega for the rest of the physics we're going to be having together. What is omega? Omega, as defined by your reference table, is the angular speed. Angular speed is defined as the quantity which identifies our speed in terms of radians per second, okay? Radians, you might recall, is part of the circle when you learned pre-calc, and the unit circle, etc. It was a degree by which we measured angle. As opposed to degrees, one could use radians to measure an angle. So what is radians doing here in oscillation? Well, we know that one complete circle is made of 2 pi radians. Similarly, in oscillation, one oscillation is made up of 2 pi radians, okay? So the angular speed in radians per second is effectively saying the speed at which we complete an oscillation, okay? So if my angular speed is 4 pi radians per second, that would stipulate that since 2 pi radians equals 1 oscillation, my speed is the same as 2 oscillations per second, okay? And so that's what our equation here is telling us. If I were to take period, and again, my angular speed being 4 pi radians per second, period equals 2 pi over 4 pi, omega being my 4 pi. And that would give us that period equals 1/2. And like I said before, period is the time it takes to complete one oscillation, so period would be in units of seconds. So on here, I determined that the angular speed is 2 oscillations per second. So if I'm completing 2 oscillations every second, how long does it take me to complete one oscillation? It takes me 1/2 second to do one oscillation. Therefore, I do 2 oscillations per second. All right, and there's a second part of this equation that says period equals 1 over the frequency, f. Frequency is how we say how many oscillations do I do per second. So this would be your frequency, where 4 pi radians per second is your angular speed, 2 oscillations per second is your frequency, and 1/2 second is your period. The next equation on your sheet is going to be T sub s, which is period of a spring. Period of a spring equals 2 pi multiplied by the radical of m over k, wherein m is the mass of your object, 2 pi is a constant, as we've discussed, and k is the spring constant of the spring. Okay, so let me ask you guys something. If I were to double the amplitude, if I were to double the distance that I extend it before I release it, what would happen to the period? Nothing would happen to the period. Why? Because amplitude is nowhere to be found in my equation. If amplitude is nowhere to be found in my equation, then if I change amplitude, I change nothing. Next equation being the period of a pendulum, T sub p, equals 2 pi times the rad of length over the gravitational constant g, okay? Where in a pendulum, in this example, the length is the length of the string that you have attached this item to, and g, of course, is the gravitational constant, okay? If I were to double the length of the string, my period would increase by rad 2. If I were to double the mass, nothing would happen to my period. Why would nothing happen to my period? Because I don't see mass in this equation. Therefore, a mass doesn't affect it. Now, our final equation here is going to be x equals big A times cosine of 2 pi ft. Okay, so that's quite a bit to unpack. What exactly is that telling us? Okay, it says that our position, x meaning position, is equal to big A, our amplitude, times the cosine of 2 pi, times our frequency, times time. And that applies to any harmonic motion. That applies to the pendulum, that applies to the horizontal spring, and in the case of the vertical spring, we would just replace x with y, meaning our position in the y direction. To be more specific with the pendulum example, the pendulum, as it moves to the left, is moving both to the left and it's moving up. Therefore, when we consider the pendulum example, we have an equation that determines our position in the y direction, and for the pendulum, we're going to have an equation that determines our position in the x direction. Okay, whereas for the springs, it's either one or the other. So position times amplitude. Here is where we see amplitude. Frequency times time times 2 pi. what we can do to simplify this equation a bit is we can pull in this guy from before. This guy stipulating that 2 pi over omega equals 1 over frequency. Doing some algebra, we can say that 2 pi divided by 1 over frequency equals omega. Therefore, 2 pi f equals omega. So therefore, we can rewrite this equation as x equals big A times cosine of omega t, where of course t is time. So let's try and think of this equation in terms of what's going on. All right. First, let's look at just the cosine section of this equation. What is cosine? Cosine is a function that oscillates between 1 and -1. Okay? I feel it would be fitting that a function that oscillates would be used to define oscillatory motion. Okay? So being that cosine oscillates between 1 and -1, going through 0 each time, you could say that the position constantly oscillates between A times 1 or A times -1. Meaning that the position is constantly oscillating between the amplitude, C, and the negative amplitude, -C. Okay? And of course, cosine always travels through 0 to get from 1 to -1, and our mass will always travel through 0 to get from our amplitude to our negative amplitude. That is what the amplitude serves in this equation. Cosine of omega times time, where omega is the angular speed. Therefore, omega defines how fast we oscillate between C and -C. And of course, the time t determines at what at what specific time are we trying to determine the position of our object. So that's the gist of this equation. Very likely what you might see on your AP exam is you'd be given some data, meaning a graph or a table, and you would say, we are unable, or rather, we are trying to determine the amplitude of such and such an oscillation. And you're given the position for different points in time, and you're given the angular speed. Okay? And what you would likely have to do is you would have to graph x as a function of cosine of your angular speed times time, such that the amplitude A would be your slope in such a graph. Let me draw that out for you so you can visualize it a bit better. If I were to graph x on the y-axis, the x position on the y-axis, and I were to graph the cosine of our given omega times time on the y-axis, then I could say that x being my y and cosine omega t becoming my x, I can write this in the form of y equals mx, which is the equation of a line where my amplitude would be m, my slope. So if I graph this, it's going to be a straight line, and if I calculate the slope of that line, the slope is going to be my amplitude. Now let's come back to what I was talking about earlier about amplitude relating to the total energy of the system. Let's look at the energy that we're dealing with in the system. At the beginning, let's say I stretch the spring out to C, to position C. That means that the spring has traveled this distance, and if the spring travels a distance away from the point at which it is at rest, it will gain potential energy. Okay, and that is defined by the equation for spring potential energy. Mu U sub S equals 1/2 K delta X squared. The distance that the spring was stretched is C, so my delta X in this case would be C squared. K 1/2 equals the potential energy stored in the spring. Okay? So where C now is my amplitude. So once I stretch it out to position C, and I hold it there with my hand, that would mean that at that moment, when it's being held at C with my hand, there is spring potential energy present, and since it's not moving, there is zero kinetic energy. Once I let the block go, the spring will pull the block back in this direction, and the block will gain kinetic energy as a result of that. At the first instant, all of the energy in the system is potential energy. At what point would we have entirely kinetic energy and zero spring potential energy? Spring potential energy is again defined like this. So in order to have zero spring potential energy, delta x would need to be 0. So the change in x from our initial position 0 would only occur when the block is at that position, when the distance between the rest position of the spring and the current position of the object is 0. So therefore, at position 0, our kinetic energy is at a maximum. All of the kinetic energy of the system represents all the energy in the system. And then as we return back to negative c, our kinetic energy is being converted back to spring potential energy. And again, we have the same amount of spring potential energy we started with, because even though our displacement is negative, a negative squared is a positive, so our spring potential energy is still positive. Therefore, by that equation, we can say that 1/2 times the spring constant k of the spring times the amplitude squared equals the maximum kinetic energy of the spring, because all of the initial potential energy eventually becomes entirely kinetic energy at the 0 position, equals 1/2 the mass of the object times the maximum velocity squared, Vmax. Okay? And again, Vmax is achieved at 0.0. How can we expect the amplitude to change? The amplitude will change if we put more energy into the system or we take energy out of the system, okay? Because putting energy into the system has to increase spring potential energy when the block is at rest and has to equal maximum kinetic energy when the block is at 0.0. In case it wasn't apparent, the block is momentarily at rest whenever it comes to either point C or point -C. Because the block is moving one direction, it slows down, it stops, and then it starts moving the other direction. It is momentarily at rest at each end of the amplitude. So if I were to introduce more energy into the system, like for example, I were to give it a little push in the same direction that it is moving at any point in the oscillation, I would increase the energy of the system. Giving it a little push would increase its velocity momentarily, and increasing its velocity would therefore compress the spring a little further, therefore increasing amplitude, and it would continue to oscillate at a greater amplitude. Greater amplitude, therefore, meaning that it achieves a greater maximum velocity at the central point. All right, that is the gist of the spring unit. Again, if you got questions, you're going to join my Discord server. Thanks for watching.